Hello. In this video, I want to give you an introduction to how to calculate moments of inertia for continuous mass distributions. And at the top here, I've just got a little bit of information about moment of inertia. A lot of this is stuff that we've discussed a little bit already. But the expression for moment of inertia drops out of our definition for torque. So if I imagine that I have say a disk here, some sort of disk, and I can imagine that disk being made up of a bunch of discrete bits of mass, m sub I. If I apply a torque on each m sub I by applying force, I can calculate the torque by the cross product of r sub I and f sub I, so r cross f, where r sub I represents the position of that mass relative to the axis of rotation. So let's say the axis of rotation is right here. And F sub I represents the force applied to that mass. I can calculate the net force, or the net torque, excuse me, on the whole object by just summing up all of the torques on the individual masses. And as it turns out, I won't derive this here, but you can show that this expression is equivalent to the one here on the right, where I have this sum of Ri squared and Mi times the angular acceleration vector. This is where the moment of inertia comes from. You'll notice here that we have an expression that says the net torque is proportional to sum times angular acceleration. That sum is what we call moment of inertia. And it tells you more or less how much angular acceleration you're going to get out when you apply a net torque to an object. So this boxed equation right here is kind of what I just said in equation form. One thing to note is that this equation is true for rigid bodies. And the reason why it's true for rigid bodies is that a rigid body, in a rigid body, all of the m sub i's, all of the individual masses in the system don't move relative to each other. So they're all moving with the same angular velocity and the same angular acceleration. So there's one single common angular acceleration vector for the whole object, which is why you can represent it this way. If you have a squishy object where different parts of the object can have different angular accelerations, this gets a lot more complicated, and this analysis will not apply to that situation. So that's one caveat. In general, the expression for moment of inertia for a discrete system, so for a discrete system is this right here, where I sum over all of the masses in the system. And we're going to convert that now to the continuous case. So that is right here. So for the continuous case, we have this integral expression where there's a direct analogy between the discrete case and the continuous case. Imagine I've got a shape over here on the left, and I've got some axis of rotation. This is an arbitrary shape, arbitrary axis of rotation. Now, instead of thinking about a bunch of discrete m sub i's, I'm going to think about a continuous distribution of infinitesimally small masses dm. And each dm has a certain position relative to the axis of rotation given by the r vector. So when I write this integral expression right here, what I'm looking at here is I've got a bunch of little masses. So dm represents a tiny mass that's part of the system or the object. And then r represents distance of dm from the axis of rotation. Basically the same interpretation as with the discrete case, but now we have continuous variables here. And so we're going to integrate rather than sum. But the interpretation is more or less the same. A couple of interpretive notes before we get into a couple of examples. The moment of inertia depends on the shape and the mass distribution of the object. So objects that have mass distributed further from the axis of rotation will tend to have higher moments of inertia. But the moment of inertia also depends on what axis the object rotates around, because depending on where you have your axis of rotation, you may cause more or less mass to be further or closer to the axis of rotation. So it's not just about the geometry of the object, it's about the geometry of the object rotating about a particular axis. And that'll be important, and we'll see an example of that shortly. So I want to do a couple of example problems. I'm going to scroll down here. So our first example, first example here, let's say I've got a rod. It's a one-dimensional rod. We've seen rods like this before. So I've got a 1D rod, and it has constant linear mass density. 1D rod, linear mass density, lambda, which is just the total mass of the rod over the length of the rod. So I'll define length here, L, and mass, M. And I'm going to choose to, or I'm going to ask, what's the moment of inertia of this rod if I rotate it about its end? So here's the axis of rotation right there. Okay. All right. So the way to approach this is to try to figure out how to apply this integral expression. So the integral expression being moment of inertia equals r squared dm. So the way to do this is to figure out what a dm is like first. So where is it and how much mass does it have? So let me say, just sort of arbitrarily, here's a little dm in my system. Arbitrary position relative to the axis of rotation. So that's dm, has mass dm. Let's say it's a distance x from the axis of rotation. And I can also say that the mass is equal to lambda times dx, where dx is just the width of that little dm. So dm has a little tiny width, which is the same as just a little tiny amount of x here along my horizontal direction. And now I can start plugging things in, because if you look at this, where r here represents the distance from the axis of rotation, here that's just going to be x, and x will vary over the length of the rod, which will point to what the bounds of the integral are going to be. So they'll go from 0 to L, x equals 0 to x equals L. And then dm, I can write in terms of dx, so it becomes an integral over the length of the rod. So let's fill all that in. So r squared is just x squared, dm lambda dx, and I'm integrating from x equals 0 to x equals L. So x equals 0 here to x equals L. And now we can do this. I can pull lambda out of the integral, and then I've got x squared dx from 0 to L. So if I do this, I get, I'll just go quickly through it, L cubed over 3. Okay? And I'm going to write that like this. Why did I write it that way? Because lambda L is the mass. So this is 1/3 total mass length squared. Okay, and that's the moment of inertia of the rod rotating about one end. You may recall the result for a rod rotating about its center is 1/12 ml squared. So I'm just going to write that so we can interpret it for a second. For a rod rotating about its center, I is 1/12 ml squared. Does this make sense? Yeah, I think so. If it's rotating about its center here, there's more mass near the axis of rotation. If it's rotating about one end, there's more mass further from the axis of rotation. So we should expect it's harder to get this particular rod rotating about its end to accelerate angularly compared with one that's rotating about its center. So the moment of inertia will be higher in the case that we considered versus the rod rotating about its center. Okay, let's look at another case. Let me separate this one out. We're going to look at the same rod, actually, but a different rotation point. So the same rod, same length, same mass, uniform mass density. So mass M, length L again. And this time we're going to have it rotate about a point outside its body. So maybe we fix it with like, you know, some thin massless pieces of metal like this. But we find some way to rotate it about that point out here. So this is now the axis of rotation out here. And I'm going to say that that is a distance h above the very center of the rod. Okay. And again, we have a constant uniform mass density, lambda equals m over L. All right, so I'm going to look at a dm again. So I'm going to choose an arbitrary dm over here. This time I'm going to choose my x differently, and maybe you'll be able to see why. So I'm going to choose x equals 0 to be here at the center of the rod, and therefore this little bit dm is a distance x from the center of the rod. The reason why I'm choosing this is because the axis of rotation is right above the center of the rod. And it's going to be convenient for me to work this way, rather than choosing it at one end of the rod, which wouldn't really be symmetrical as I go from one half of the rod to the other. But the r, if I write my integral expression, integral r squared dm, the r is a little bit trickier than the previous case. It's not just x. I have to consider that the point is h above the rod as well. So the actual r vector is this right here. That's r. And the magnitude of r squared, well, it's a Pythagorean theorem, x squared plus h squared. So I can make a little triangle where r is the hypotenuse, and the magnitude r squared would be just x squared plus h squared. So the magnitude of r varies over the length of the rod as x changes in this way. Again, dm is just going to be equal to lambda times dx, where dx is just the length of our little infinitesimal mass. Okay, so let's plug this in. So I've got I equals integral r squared dm. And if I plug in these expressions, r squared is x squared plus h squared. Dm is lambda dx. And now what are my bounds? Well, I guess I have to pick what's positive and what's negative. So if positive x goes to the right, then I'm integrating from negative L over 2 over here to positive L over 2 on this side. So I'm integrating from negative L over 2 to positive L over 2. And let me reorganize this a little bit. So I'm going to pull out lambda, x squared plus h squared dx from negative L over 2 to L over 2. And I can do this integral. So lambda times x cubed over 3 plus h squared x evaluated at the bounds minus L over 2 to L over 2. And now we've got to plug stuff in. It looks kind of ugly at this point. It'll end up looking a little bit nicer when we get to the end. So let's plug some stuff in. If I take the first term first, so if I have x cubed over 3, I'm going to get the upper bound plugged in minus the lower bound plugged in. The lower bound is the same as the upper bound with a minus sign. The x cubed returns a minus sign on the lower bound. So I'm going to get the two terms actually being the same and adding to each other. You can check my work here if you want, but I'm going to write this down. So it is lambda times 2/3 L over 2 cubed. And you can check my work there. The second term would just be h squared times L times lambda. Forgot a lambda in there. Okay, you can check my work there. If we look at this fraction here, I've got a 2 over 2 cubed. So that's 2 over 8, which is 1/4. So in the bottom, I get a 12 and 1 on top. So I'm looking at lambda L cubed over 12 plus lambda H squared L. Okay, now let's recall that lambda is M over L. So the mass is lambda times L. And therefore I can write this as 1/12 mL squared plus m times h squared. That's my moment of inertia for this rod rotating about this point h above the center of the rod. Kind of an interesting result. You'll notice actually that we said the moment of inertia for a rod rotating about its center was 1/12 mL squared. That's present here, but there's this extra term for the distance that the axis of rotation is above the center. We'll talk briefly about the parallel axis theorem at some point, but for now I'm just going to note that as an interesting result. And you can investigate the parallel axis theorem on your own if you want to kind of understand this result a little more deeply. Okay, one more example I want to show you, and this for a two-dimensional object. So give me a second to pull up that diagram. Okay, so here I've got a disk of mass m with uniform mass density sigma. This thing's a sigma right here. Usually we would use this for an area mass density. Sigma equals the mass of the object over pi r squared, the total area of the object. You could conceptualize this as a thin disk that's really just two-dimensional, or a cylinder that is uniform in its depth dimension. So effectively every layer of the disk has the same uniform mass density, and it's just a cylinder of some depth. Turns out the result is the same. But we'll just imagine this is a purely two-dimensional object here. So how do I approach calculating the moment of inertia in this case? So I've got this integral expression r squared dm. The way to approach is really the same. The mechanics are a little bit different, but the idea is the same. So I'm going to choose a dm. Here's a dm that we're going to look at. So this is a little bit of mass, infinitesimal mass. And the goal will be to figure out how to represent that mass. So there's some dm. There's some dm there. The little red square has a little bit of mass. The mass will be equal to the mass density times the tiny amount of area that that square has. Now this really is a rectangle, not a square, a rectangle. And there's some dimensions to it. There's some, say, width to it, and there's some height to it. If I can get the width and height of this rectangle, I just multiply those together to get the area. So let's try to figure that out. Well, if I imagine I've got, say, some distance away from the axis of rotation, and I think I forgot to say that we're going to have this rotating about the center here. So we're rotating this disk about its center. If I've got our little dm some distance away from the axis of rotation, r, well, then I can just say that the width here, or the height, I guess, is dr. So some little amount of my r variable here. I can also say that there's a tiny amount of angle right here that represents how much angle is covered by my little dm as I go around the circle. That means that the arc length covered, which is the same as this width, is r d theta. So just taking the arc length as r d theta. And remember, this is an infinitesimal thing. So we can imagine that the length here and the length here are the same, and that r here and r here are effectively the same. Okay, so what's the area now? Well, dm is going to be equal to sigma times the width times the height. So r d theta times dr. So I've broken down an area vector into two an area vector, excuse me, an area infinitesimal into two sort of length infinitesimals, r d theta and dr. And we're going to plug that in and see how to deal with this. We're going to end up with something called a double integral. So I'm going to plug stuff in. As it turns out in this case, the r squared in here is really just r squared, because my dm is just a distance r away from the axis of rotation. That's kind of nice. So I've got r squared, and then I plug in my dm, sigma r d theta times dr. And now I have two variables that I'm integrating over. I'm integrating over both theta and dr. And the first step of doing a double integral is adding a second set of bounds. In one set of bounds, I'm integrating over theta. And I'm going to integrate all the way around this circle. So my theta is going to go from, say, 0 to 2 pi as I integrate around the entire circle. So 0 to 2 pi are the bounds for theta. And then my other bound is I'm going to go from the center of this circle all the way to the outside. So I'm going from little r equals 0 to little r equals big R, the full radius of the circle. So my bounds for my dr integral are 0 to big R. So I have two sets of bounds. And the trick here is just to evaluate each integral one at a time. I'm going to write this a little bit differently. So 0 to r cubed. I can pull sigma out. So sigma integral 0 to r cubed dr. And then I just have this other integral 0 to 2 pi d theta. You'll notice that this integral does not depend at all on r, which is kind of nice. The only thing in the whole integral that depends on theta is the d theta. And for the purposes of doing a double integral, I can think of just doing two single integrals one at a time. So imagine that this part didn't exist and do the d theta integral. You just get theta evaluated from 0 to 2 pi. And so the result of that would just be 2 pi. And then we're going to evaluate this, multiplying by that 2 pi. So I do the first integral first, and my d theta integral first, sigma r cubed dr times 2 pi is the result of this integral by itself. The 2 pi I can pull out of this integral. So 2 pi sigma, because it's just a constant. Forgot the bounds here. 0 to r cubed dr. And now it's just a single integral again, r cubed dr. We know how to do that. I is equal to 2 pi sigma r fourth over 4, 0 to r. So pi lambda over 2 times r to the fourth. I'm going to write this a little bit differently. So I'm going to write it as sigma pi r squared over 2 times r squared. The reason why I'm writing it that way is because sigma is our mass density. So the mass is sigma times pi r squared. That's this. That's the mass. That means that I can say that the moment of inertia is 1/2 mr squared, and that's the result. There are other ways to approach this problem where you exploit the symmetry of the disk to turn this into a single integral, and we can talk about some of those approaches later on. But I wanted to give you an introduction to double integrals because it'll be useful to know how to do them going forwards. And we'll have a little bit more practice at that coming up. So I hope this was helpful, and I'll talk to you soon. Okay, bye.